Welcome to The Explainer. Today, we're going to cut right through all the hype around AI and get down to what it actually means for mechanical engineering. You know, how it's really changing things from the ground up. Okay, so you hear these terms thrown around all the time, right? AI, ML, DL. It's easy to think they're just buzzwords, but we're going to demystify them and show you how they're translating into some serious, real-world engineering breakthroughs. So to really get a handle on the impact here, we first have to get the concept straight. And honestly, the best way to think about it is like a set of those nested Russian dolls. So AI, that's the biggest doll. It's the huge, overarching idea of making machines smart. Smart enough to look at a situation, analyze it, and figure out the rules for themselves, without us having to code every little step. Now, nestled inside AI, you've got machine learning, or ML. This is where things get really interesting. Instead of explicit programming, you feed the system tons of data, and the algorithm itself learns to spot the patterns. It starts to see that, hey, when these inputs happen, this outcome is super likely. And then you have the smallest, but maybe the most powerful doll, deep learning. This is a special kind of machine learning that uses these complex neural networks. It's the engine behind some of the craziest advances we see today, like a computer being able to instantly recognize what's in a picture. So how do these systems actually, learn? It really boils down to three main approaches. First, you've got supervised learning. Think of this like you're a teacher, giving the AI a bunch of examples with all the correct answers labeled. It's perfect for things like classification. Then there's unsupervised learning, where you just dump a bunch of data on it and say, go find something interesting. It's fantastic for spotting weird anomalies you didn't even know to look for. And finally, there's reinforcement learning. This is pure trial and error. The AI tries something, and if it's a good move, you give it a reward. It's exactly how you'd train a robot to solve a maze. All right, so we've got the concepts down. Now let's see how this all comes together to have a frankly staggering impact on actual engineering design. You know the drill. Standard engineering tools, things like finite element analysis, computational fluid dynamics, they are incredibly powerful. But they work by solving these hugely complex physics equations, and man, are they slow. We're talking hours, sometimes even days, for just one single design change. But what if, instead of solving the physics from scratch every single time, an ML model could just learn from thousands of those past simulations? Well, it can. And it can predict the outcome almost instantly. And here's the crucial point. What we're talking about is an acceleration factor of around 100,000 times. I mean, let that sink in. This doesn't just speed up the old way of doing things, it completely shatters it. It unlocks things like generative design, where an engineer can explore thousands of completely new design options overnight, something that would have taken a human team years to even attempt. But, okay, there's always a catch, right? And here it is. The ML model is an approximation. A very, very good one, but it's not a perfect physical solution. So the way engineers use it is for that crazy fast exploration up front, and then they take the best few designs and verify them with a good old-fashioned full simulation. This incredible speed isn't just for the design phase either. It's also totally revolutionizing how we keep machines running out in the field and, hopefully, how we prevent those catastrophic failures. The whole goal here is to switch from being reactive to being proactive. Instead of waiting for something to break, which is always expensive and happens at the worst possible time, you use sensor data and ML to see the signs of wear and tear long before it leads to a total shutdown. And as you can see here, this isn't some magic wand you just wave over your equipment. Implementing predictive maintenance is a rigorous, structured engineering program. It starts with feasibility studies, selecting the right machines, and it goes all the way through to analyzing conditions and making corrections. It's all about focusing your resources where they're going to deliver the most bang for your buck. So all of this sounds amazing, right? But of course, these powerful tools don't come for free. They bring a whole new set of challenges and, frankly, responsibilities that we as engineers have to navigate. Yeah, adopting these tools isn't exactly plug and play. There are some serious hurdles to get over. First, there's the massive cost and effort of just generating enough high-quality data to train these things. Then you've got the black box problem. How do you really understand why the model made the prediction it did? And you always have to watch out for building a model that's great at predicting your training data but useless in the real world. And this quote just hits the nail on the head. You've heard garbage in, garbage out, right? Well, with AI, it's that principle on steroids. The performance, the reliability, the safety of the entire system, it all comes down to the quality and the breadth of the data you feed it. Getting that right is now a core engineering responsibility. So, when you put this all together, we're left with a really fundamental question about the value of this incredible new capability. It's all about a critical trade-off. So I'll leave you with this to think about. Where does that massive 100,000x payoff in speed most outweigh the potential risk of a slightly less precise answer? Is it in that early, wide-open phase of design exploration where you're just trying to find new ideas? Or is it out in the field, trying to prevent a machine from failing? That trade-off, that's really at the heart of the entire engineering AI revolution.